Okay. Kind of try and take a breath or whatever and shake it out. You hear my voice a lot. I think I have 2 more sections to go before we hit lunch. We'll go through site location. And this isn't going to be, this is how you pick a site. This is going to be kind of, well, here's where we're collecting data. Has anybody seen a paper that says, here's what a test site should look like? Oh, thank goodness. That was the worst paper we ever published. And it wasn't, technically it was never really published. It went into an SPIE. Oh, Cindy is here.
What?
I thought you moved locations. You can't do that to me.
Yeah. What a test site should look like? Yeah, you should just follow every single one of them.
Yeah, well, no, I proved that, or I basically showed that not many have seen that paper, so I'm in good shape. They haven't been confused by this is exactly what you should do. These aren't even checklists, these are not guidelines, these are just conceptual things. And the whole goal, again, is we're trying to reduce uncertainties. And the way you will reduce uncertainty is understanding how the reflectance of the surface couples with the atmosphere and gives you a top of atmosphere radius. What's nice is you can pick a test site that really helps you reduce your uncertainties. And that's what you're after. Now, by doing that, it could be going to a really bad test site a lot more. That can reduce your uncertainties, especially if you can show that you have a random variability. If you have 4 measurements that are truly random, you just improved your results by a factor of 2 over having only 1. So there's no perfect answer in terms of a single test site. I tend towards going for high flat spectral reflectance. It allows me to band average easier. Large size with spatial uniformity makes it easier to sample. It also makes it easier in the rate to transfer. Low aerosol loading means I can get lazy and I don't have to really characterize the atmosphere very carefully. And the one that gets lost is accessibility and some kind of historical understanding. If you can access it readily, then you'll get more data. One of the things that helped the group in Arizona was we went from doing 4 campaigns over 5 years to doing 4 campaigns over 1 month. And that kind of sampling wears you out and gives you a lot of data, but at the same time it helps you understand the problem better. Your choices of the rate to transfer code, aerosol model, all of these are important, and we're to a point now where these are going to start to become more important, but they're all at that 0.5% to 1% on a 2.5% total error budget. They're not as important as the site selection. So, again, just to reiterate, if you go to certain atmospheric and surface conditions, you get some uncertainties that are reduced. So high reflectance, low aerosol amounts. That really makes everything simple. Spectrally flat reflectance, spatially homogeneous. Clear skies. Especially if it's not a very close site, if you have to drive or fly to get to the site, and it takes you 5 to 10 hours to get there, it's really frustrating if it's cloudy all the time. So finding someplace that's clear is very helpful. And I can talk about colleagues I know from Japan who periodically come all the way to the United States, they come out for a week, and they get no data because it was cloudy the whole time they were there. It's a very frustrating problem. High altitudes gets rid of some of the atmosphere. The large test site, again, adjacency effects, things that you get scattering from outside the view of the sensor. There is no perfect site. Don't look for it, don't try to find it. You can spend months searching through imagery of Landsat looking for the perfect site in Australia. It will never happen. Cindy will prove me wrong later in the course. So.
No, he's right.
All of these, it's basically, you choose where your uncertainties are. So one of the reasons we had problems with Landsat was we picked a high reflectance site that was at a low latitude. So we had very high radiance values in the summertime, which caused an optimization problem, which caused a weird effect that gave us a 2%, 1% effect between 2 clusters of data. If I had picked a darker site, this would have gone away. But my scatter might have been larger because of atmospheric influences. So you pick what's going to cause you problems in all of this. And that's kind of what the discussion will happen over the next several days in terms of uncertainties and error budgets. I'll present you what I know to be the uncertainties, and then you start, especially when we go through the practical part of the course, you take all of that and decide which uncertainties am I more concerned about, and which site do I want to use in that case. So there's man-made sites, both asphalt, and this is fresh asphalt, and this is old asphalt, so it's gray and black. This is about 0.1 reflectance, this is about 0.2 reflectance. It's fairly straightforward to characterize. The reason we chose this site was it was only a 30-minute drive from our building where I was in Tucson, Arizona. So we could go there for every overpass of Landsat if we wanted to. TARPs. There's also a site north of, I think it's north of here, Alto. Is that north or south? I'm American, I know no geography beyond what's happening in the United States. But there's a site where they put out gravel that are varying reflectances. We do the same in the United States, we painted areas. These are large pieces of fabric, tarpaulins, that they put out. And again, you can get different values, you can see them up here. There's advantages to man-made sites. You can control the reflectance. You can have them in places that are easy to get to. But you have problems with them in that they're not very large. And so you have to have a sensor. Those tarps in the right-hand image are not going to work for Landsat, but they will work for GF1 and they will work for Iconos and QuickBird and Worldview. Natural sites. Well, natural sites are is you have to rely on nature to create them. In the United States, we have a lot of dry lake beds. So what happens is these areas either flood, and then as the water evaporates, the sediment's left behind. In the case of Railroad Valley, it actually is an underground spring that basically many, many years ago came up and flooded and brought all the material with it up to the surface and then dried out. But you get some very odd features, cracks and things. You can pick places where the skies are very clear and very easy to characterize. You can pick areas that are very flat, very uniform. So now I do not have to worry about cosine zenith angle effects. I don't have to worry about topography. I don't have to worry about vegetation at this location. I get something that's very easy to characterize. But they can be far away. Rio Blanco in Argentina is not an easy trip for somebody in the United States. Whatever it is, it's important because we don't need them to be constant with time. We just need to be able to get there and characterize them because in some cases it can snow. And this actually ended up being a perfect situation at Railroad Valley where we were calibrating a system that was only in the visible near infrared. It was a worldview case. And it was high resolution. So all I did was I stood at the panel, did my panel measurements, and I just turned, and then I turned, and then I turned because it snowed 15 centimeters the night before. Fresh snow, brand new, thick enough that I could see the bottom. And all I had to do was take one measurement and not move at all. And we got the best calibration we ever did because the skies were perfectly clear, perfectly uniform, and it was very bright. So that was, it would not have worked if we needed shortwave infrared because the snow is dark in the shortwave infrared. But this lucky, it just sometimes happens. Other cases, we end up with actual water on our lakes in Railroad Valley. This is what happens when somebody much younger than you is in charge of driving a vehicle. And they decided that they just wanted to keep going back. They just went back and forth through that mud. And I had to pay extra to have it cleaned before we returned the vehicle, but it shows that you have to somehow characterize the surface every time. Because the sites we're picking, at least that I was picking, were not constant with time. They can change because of rain, because of snow. The tarps, you put them out because again it makes it easier to find where these sites are. If that was not there, you'd have a very difficult time, especially if spatial resolution is around 30 meters or larger. It becomes very difficult to pick out features. No matter how many times you go to a test site, it still becomes difficult for bonus for me at Railroad Valley to find the one pixel that we characterize.
Can I ask a quick question? You said you have to go back because it changes with time. You've got years and years worth of data. Have you seen a lot of correlation, seasonal correlation in the data?
So the advantage to the sites in the western United States are if you get in the summertime, and it has not rained for more than a week, the reflectance is year to year identical, and within a few percent.
But that allows you also to do it historically as well.
Well, that's what I'm saying. So from 1995 to 2015, they're still collecting data there. Between June and September, if you can show that it has not rained, the reflectance of the site is constant to within a few percent.
But I mean, you could also go backwards before that.
And that's where you then have difficulties. And so that's what we're trying to do is we're trying to do it from a physical standpoint. That if you can show certain measurements back in time that give you confidence from some other system like spectrally, or there's some other information that allows you for the morphology of the material that allows you to do that. We're trying to do that with the Libyan desert. We have difficulties. If you go back far enough with the Libyan desert, you start to see some trends. And we're not sure if it's real or instrumental. And the climate changes, some of these sites will change, and that's the difficulty. Geolocation, pretty straightforward again. This is Railroad Valley, not Ivanpah. You can see the tarps. These are 1 meter data. The vehicles typically are parked here. We would walk this region. There's a rectangle that we're covering. And that's enough to give you information about basically what you would have to do to then compare to the top of atmosphere radiance prediction. Talk a little bit about the solar radiation. Solar constant is not well understood at the spectral level. I think I talked a little bit more about that this afternoon or tomorrow. Maybe it is just here, but you'll find multiple solar models that are available. Matran, if you run Matran, there's 5 or 6 choices. Within there, the Chance, Courage model, the checker model is the way they call it, is typically the accepted one that most people use. WRC is the World Radiation Council value, and that's the older version. And then there's a newer version by Fourier, which is based on measurements from the space shuttle over time. What I'm showing here is basically just the output of these different models as a function of wavelength, and on the right is the percent difference averaged over 10, 50 nanometer, 100 nanometer spectral windows. So you start with, in here, these 2 features. Those are the Fraunhofer lines and the solar outputs, the calcium absorption in the solar atmosphere. And the Matran, because the Matran has a higher spectral resolution, has a deeper feature. Now, if you band average across that, the impact's not that large. But there are other features between them. As you get out to the shortwave infrared, and you can have 7–8% differences. So if I were to do ASTER, for instance, which I think we changed the plan, but it was based on the WRC originally, because that was the NASA version. And if you then compared that to Landsat, which is using Matran, and you had 2 bands that were the same, they would differ by 7%, simply because of the solar models that were chosen. That's the entire error budget right there. Now, we never found out that that was true because ASTER, the bands where this is important, had a stray light problem. So we never corrected stray light at a level that allowed us to do the comparisons between MODIS and ASTER. And so it was frustrating, but we never could prove it. But at some point we have to figure out what is the true solar model. And this is important because the Vicarious method needs a solar model in the rate of transfer code to get to a radiance. And it's not bad because if you then use that same solar model to divide out to a reflectance, you're in okay shape. But it still can create some interesting differences. For ASTER, if I do the calibration, early on we had some differences here. The 0% lines, the 3% uncertainty is what we think we have for the methodology. So we thought we had some differences between us and ASTER and those bands. Those have been fixed. Get out to the longer wavelength, the short wavelength infrared, the agreement's a little better, but you notice that depending upon which solar model I pick, I can either get agreement or not agreement. And the longer wavelength, these 3 over here, I'm not sure I trust, especially band 9. There's an optical straight light problem we have to worry about. But band 4 and 5. 5 is an easy one to look at. If you use the WRC, pretty good agreement. If you use Modtran, the agreement's not so good. And what that means is, and what this really showing is, which solar model is most likely consistent with the pre-launch laboratory calibration that was done. And in that case, I would have leaned toward WRC because they're following the standard methodologies that are being used for laboratory calibration against standard lamps of solar or spectral irradiance. Whereas the Modtran it's a completely different pathway in terms of its traceability. But more people tend to believe that Modtran is one that's probably closer to reality. So it's an interesting question that has to be answered at some point. For us right now, you have to carry that as part of your uncertainty budget. And at the same time, you just have to make sure that you're being consistent. If you're calibrating a system where the users are using Modtran, then use Modtran in your Vicarious, and you'll be fine. So when I do my Landsat talks, I use Modtran. It's the last thing I do. At the very end, I multiply everything by Modtran. If I'm doing Aster, my last step is I do WRC. The very last step, I just multiply by WRC. And then it's all consistent. All right. TOA radiance and the reflectance determination. So this is going through a little bit of the range of transfer kind of background before we take a break for lunch. I think this is the last one of this session. The processing codes that we need, the Langley, modified Langley, we'll basically get all of this as we go on. Beer's law, aerosol inversion, surface reflectance, panel BRF, surface BRF, and then the radiant of transfer. What we're trying to do is take energy from the sun and energy from the atmosphere to the earth and figure out what's happening at the sensor. So this includes basically solar reflective and thermal infrared. What's nice is I can immediately get rid of, for this training course, purple. And I'm only going to worry about the easy part. I was raised because my advisor was reflected solar. The thermal is the easy part. So it all depends on who you talk to. But you basically have energy from the sun, and the most straightforward path is directly from the sun, through the atmosphere, hit the ground, back through the atmosphere. If I only had that turn, all I would need to know is the transmittance of the atmosphere and the reflectance of the surface, and I could predict what's happening at the sensor. The difficulty is that if you look out the window, you can see light. If this were the only turn that we had to worry about, this one right here, and this one, if this was the only turn we had to worry about, the sky would be black even during the day. Because the sky isn't black during the day, we have to worry about cases where now I'm over here, it hits the ground, hits something in the atmosphere, it goes to the sensor, comes from the sun, hits something in the atmosphere, comes to the ground, goes back up, and then I've got the ones where it comes in, it just hits the atmosphere and goes back up. And I can do these in upright. I can have it where it hits the atmosphere and the ground, then the atmosphere again, the atmosphere and the ground twice. And that's where the difficulty comes in. That's why the range of transfer codes are so difficult to comprehend. Is there's all these weird little pathways that can happen that we have to model. So the level of radiance at the sensor, and hopefully this makes some sense, depends on surface, how bright it is, the atmosphere, what's in it, how much of it, and the geometry, sun angle, view angle. Larger optical depths. Okay, so we'll talk about optical depths later on this afternoon. That's about the amount of stuff in the atmosphere. So I have more stuff in the atmosphere, and that's usually the case at short wavelengths and longer paths. Then I get more scattering, I get more effects. So what's happening out today is I basically have more stuff in the atmosphere that's causing scattering. Higher reflectance. The brighter the surface, the higher the radiance at the sensor. That one should make a lot of sense. So we'll always come back to that one as kind of the basic. The rate of transfer is nothing magical here. It's just trying to figure out what each of the pieces are in terms of the components that they add to the system. The more direct solar is what you also get in that case. So if I have a very bright surface, all of these other terms that hit the atmosphere aren't as important. And that makes the range of transfer simpler. So even if I have a code that's not that good, if I'm dominated by that direct solar term, my answer gets better. Angular dependence. So the reflectance, phase function is basically the scattering by the particles in the atmosphere. That's a directional effect. View angle path length. If the sun is coming through at a very large zenith, it has to get through much more atmosphere with more chances for scatter. If my sensor is looking at a large angle, it has to come through a lot larger atmosphere. There's a better chance of getting scatter. So that makes the problem tougher. The easier problem is looking straight down and a high sun angle. Small solar zenith. Topography plays a role. Cosine effect at the very least. So you get the tilt of the surface, and now you have a cosine effect because of the sun angle on the ground. At the same time, as you change elevation, you're also going to change the amount of atmosphere. And so both of those will play a role. So there's an easy way to solve this problem, is to go someplace flat. Now you know I like flat surfaces because even if I have, if it's even tilted a little bit, what's nice is if you have a dry lake bed, you also feel pretty good that it's flat relative to horizontal, because the reason it looks the way it does, it was filled with water, all the sediment settled out. Well, the water basically it's following the gravitational form of the earth, and then all the sediment basically ends up flat too. So you end up in a nice situation where you're not only flat, but you're truly horizontal. So all you have to do is solve this equation. That's it. So your top of atmosphere radiance is just this three terms, basically. It's the path radiance, the downwelling solar, or the downwelling irradiance from the whole sky. So this is all the skylight that's coming down. And then this term is the direct solar. It's the amount of energy coming from the sun through the atmosphere, hitting the ground and going back up. The reason I love this equation is the term that looks the worst, this is the only one that's truly determinable. This is the only one we can measure and answer. These other two, we can only guess. We can only play games with numerical integration, with iteration techniques, with Monte Carlo approaches. This is the only one that I can actually get the right answer to. If I know all the inputs. So all I really have to know is, what my geometry is, what the amount of stuff in the atmosphere is, the solar zenith angle, the pathway from the sun, the amount of energy from the sun, and the surface reflectance. And I can calculate that. And this is important, because when you start working a problem, especially if you're working with a range of transfer code the first time, you can pull out a calculator, you can pull out a spreadsheet, you can do this calculation yourself. And if you're dealing with a longer wavelength where you don't have much scattering, and you're dealing with a bright surface, you'll get within 10% of your right answer without having to do all this fancy stuff over here. And so being able to do quick scale analysis of different terms or sensitivity analysis allows you to check and see, am I doing something really bad with some other part of my code? Have I got elevation or zenith angle in my code? And the number of times I've gone through this myself has been, I can't even count it anymore. And it's simple things like Modtran. Every time I run Modtran again, my first thing is I go to the top of the atmosphere and I tell Modtran to go look up. Because if I'm at the top of the atmosphere and I'm looking up, my radiance should be, anybody want to guess? 0. I'm at the top of the atmosphere and I look up to space, I should get 0. Unless I did the geometry wrong with Modtran. Because Modtran, I can never remember if they use zenith angle or if they use elevation angle. If they use view angle and nadir angle, and I never know if the heights and the H's and the zeros. So I always put it in, I look up, and then just to make sure I go to the bottom and I look down and I know what I have from the Lambertian surface and I can calculate these things manually. And it's always a little bit of help there. So that downwelling sky air radiance term is non-trivial, and it changes with time. So here's an all sky, and so I covered up the sun. This is basically energy that you have to account for that's coming down onto the surface and reflecting and going back up. And in some cases, it can be very difficult to calculate because it can vary spatially, it can vary temporally. This is an easy day to work with in reflective space calibration. This is a day I hope you do not have to use for reflective space calibration. Now, you may have to because this may be the only data point you have the whole year where there was even any sunlight. I always look for these places because I did not, so the number of times I went to a test site and just walked away when it looked like this is, again, more than I can count anymore. But it's all in terms of trying to simplify the calculations for what's happening here. And we can see these in real data. So these are MISR. MISR is a multi-angle look system. So on the left, it's looking straight down, and on the right, it's looking out at about 60 degrees. Can't see much atmosphere, can't see much atmosphere. I'm starting to see some haze and smoke. And over here, I'm seeing a lot of radio scattering. It's a 3-band color mix. MISR operates in the visible out into the near infrared. And so this basically, they did a combination of their blue band, green band, and red band. Yeah, because I'm not seeing red vegetation. So it's almost a true color. And this is almost all from band 1, where you get an increase in the scattering. You also have, if you look carefully, here you can see a difference in the way the surface appears. I'll switch on this side for other people. And that change in the way the surface appears is partly because of the atmosphere, but it's also because of bidirectional reflectance effects, which we have to take into account. But if you have a good rate of transfer model, and you have an understanding of what's in the atmosphere, this one's a little trickier because of this haze, you can model this whole effect right here. You ought to be able to take this image on the left-hand side and predict that right-hand image over there if you understand what's in the atmosphere and what the surface is doing. And you can see it in other places. Right here. And you have to know what to look for. Normally, the water looks blue and the clouds look white. But when clouds look brown, that's most likely dust. And several of you probably figured out the geometry here. This particular case is on the left. Basically, we have China over here and the Pacific Ocean and the west coast of the United States. This right-hand image is a different image. This is Africa. So this is coming off of, I think, the Gobi Desert. And so it's the yellow sand dust storms that tend to happen and then make their way across the ocean. But you can see it because you have a dark surface. If you do not have a dark surface, it becomes much more difficult to see that atmospheric effect. If I go to where the surface is dark, now I can see that atmospheric effect. This is the real part of rate of transfer. This is what got me into rate of transfer. I can go outside and I can look at the sky and I can see the photons and I can see what's happening. It makes sense to me. I can tell why the sky horizon looks brighter than it does looking straight up. For me, looking at this imagery is why I got into remote sensing, because it's there. You can tell what is happening, and you can pick out the bits and pieces. So rate of transfer code complexity is such that we then end up using numerical methods. So I talked about Gauss-Seidel iteration. I suspect almost nobody knows what that is anymore. But if you have a problem that's intransitive, where you basically have to know the left hand and the right hand at the same time, you can iterate back and forth. And Gauss and Seidel figured out a way to do that and developed a numerical method, and then you can put that into a computer code and do that. So we solved the rate of transfer equation using that iteration. Monte Carlo techniques are very similar as well, as you basically do probability distribution functions to do the calculations. Other things we play, we make approximations. Ocean color community, they know that they're not getting much from the surface, and so that allows them to concentrate on some of the other pathway terms. Modeling portions to reduce dimensionality. The 6S code does this without you really knowing it. Buried deep inside there is an approximation to all the calculations in the atmosphere that are done in azimuth that simplifies the problem. Each of the codes has their own idiosyncrasies, and they will differ by about 1%. I defy you, though, to take 3 codes and come up with a way to make the inputs identical for all 3 codes. And that's what causes most of the differences. One code may say, give me the surface pressure. The other one will tell you to give you the actual molecular optical thickness. So if you want to make them identical, you have to start iterating on the pressure in order to get to the same optical thickness so you can compare the two codes. And the same thing happens with the aerosol. One will parameterize the aerosols in a different way than the other. So it's not so much that the codes themselves differ, it's the way they take the inputs for the atmosphere and the surface that causes them to differ from one another. For us, it's not going to be a big deal. I've mentioned this once, I'll mention it again, it's going to happen a few more times. For under clear skies, bright surface, pick whatever's being used down the hall. It really is the best way to do it. So again, it's not limiting. I've used all of these, DyeSort. I happen to know the guy. What's nice is the reason I like DyeSort is because he works with me on the Terra team, so he's one of my deputy project scientists. Eric Remote is at Goddard. I worked with him, and the 5S code was done with his advisor, and so I know that group out at LOA in France, in Lille. And then the Montran is basically using the DyeSort, so I sort of know them. It's a very small community, so if you're in the radiation transfer community, you figure out that there really aren't any wrong answers. The key inputs, we've talked about that already, and what is really important is knowing the code well enough that you can figure out what the problems are for that particular code. For instance, Montran. Montran is fantastic. You could use it for a cloudy day like today with a sun angle of 85 degrees and a view angle of 75 degrees. The code will perfectly be happy to run. If you give it those inputs, it will give you an output. If I ever, I'll take names and I'll keep track of you throughout your career. If I ever see anybody using Montran for that particular case, I will come and find you and try and find a way to have them revoke your dissertation or try and find some way to penalize you because it's an improper use of a code. And that's really what you want to be understanding is your uncertainties. You want to get the error budgets, the uncertainties known of how you use these, not whether or not it's the right answer. The one last step we have to go through is band average. Have it here as a formulation so that you know that's there. But we get TOA radiance, we can do whatever interval we want. We can do 1 nanometer across the spectrum of interest, and then we have to then figure out what's going on with a particular band. You can take center wavelength, you can take a rectangle function, just average, or you can do the full integrations and then figure out what the true mean radiance is within a given band. So this just gives you a formulation for doing it. The bottom one is what you want in terms of spectral radiance. It includes your spectral response of your instrument. And if you've never seen this before in terms of an average, the average of a function is basically that function integrated over your averaging term. So in this case, we're averaging over the spectral response of the filter, and there's the radiance. It's just a straightforward integration. Cindy, do you want me to have this one last one here?
How long do you have?
I can do it in 15 minutes.
Yeah, just go for it, I think. The food's out there.
It starts, with a good one. This will make people chunk.
It's really cool, yeah.
It's,
I think I've seen that.
well, they may not have seen it. It's one of my favorite ones. This one you saw. But this is the point of if you're out in the desert and it's hot, you start doing things that don't make a lot of sense. And it's the point that in terms of uncertainties and outliers, there are real effects. There's different surfaces like snow, there's dust storms, there's smoke, and there's just really bad users. And ultimately, somebody has to carry the spectrometer, somebody has to set up the panel, and if they think that's funny, then you might want to consider sending them to NASA Goddard and never using them again. We always point out that the people that are watching are probably as important as the people that are collecting. In terms of user and instrumental errors, how you operate, where you stand. We're not really thrilled when the person who's watching the other person stands that close to a panel. And fortunately, it turns out where they were standing wasn't that big of an issue, and they hadn't really started collecting. I told them to move. How you stand relative to the panel plays a role, and for us it was repeatability, it was also a methodology in developing the techniques, and so you have biases depending upon, does someone need to be told what to do, or have they done it so many times that they need nobody else around them to be able to do it properly. So there's techniques that come in terms of repeatability and in terms of doing it right, because that's the good science way of doing it. And both of these are important for reflectance-based calibration. Absolute versus relative. I kind of talked about this on Tuesday, and if you missed it, it's repeatability. I will use interchangeably with precision. Absolute accuracy are related to biases, and in terms of the reflectance-based selections of aerosol types or amounts. Other errors we don't really worry about, but the precision and repeatability is really how well you do in terms of, does the aerosol change at a test site? So one of the nice things about Railroad Valley is for 350 days out of the year, the aerosols are always the same. And then there's 15 days where you have to worry about smoke. You just ignore those days and your repeatability gets much better. You have to have enough data that you can eliminate those days, but for us it was always the case. The accuracy of the solar radiometer, it turns out that creates a bias eventually, but the calibration is a relative calibration. But understanding whether you have an absolute or a relative uncertainty problem is what's going to then get into the discussion of how you treat it, whether you're doing repeatability or whether you're actually trying to compare from an absolute radiometric standpoint. So for the atmospheric side, we'll talk, and all of these will get more details. You'll hear it today or this morning, and then you'll hear it again later on in the detailed sections. Calibration in terms of the instruments that we're using, and the retrieval is the solar radiometer. So it's the errors and how we calibrate them. It's the sensor itself that changes. The errors in the instrument calibration will get us an uncertainty in the optical thickness, the amount of dust in the atmosphere. And then that changes the rate of transfer, which then changes the topographic radiance prediction. Buried in there is also the composition, how well the aerosols absorb, and that'll become important. The test site, we talked about this. What you pick for a test site will impact your uncertainties. If I'm worried about adjacency effect, scattering that comes up from the surface around my test site, then Railroad Valley is a much better site because it's bigger. It's 15 kilometers, they're both the same scale. So Ivanpah Apply on the left is about 2 kilometers across, Railroad Valley is about 15 kilometers across. What's interesting is Railroad Valley is a little bit higher latitude. So if we were doing geostationary system, Ivanpah Apply would be a slightly better place to go. If we're doing Avarice, Ivanpah Apply is a better place to go because it's closer to JPL. It's also closer to Ames. So there's where they're flying the aircraft from. So there's all these different things in terms of heterogeneity and reflectance. These two sites are equivalent for what I do. They're both big enough and the atmosphere is clear enough that I do not have to worry about the rates of transfer being different between the two of them. They're usually big enough that the sensors that I'm calibrating are not an issue. So MODIS is difficult on the left because it's a 1 kilometer footprint. But I can do pretty much every other sensor at both sites. And I should not get a difference in results. View angle effects. Some sites you get large view angles. If it's a geostationary looking at northern latitudes, you get a large view angle. Typically you get larger uncertainties in those cases because of the path length. You're more sensitive to atmospheric influences. Surface PRDF is a bigger problem. You have to figure out a way to remove that uncertainty, to make that not be important. And we can figure that out through the range of transfer code and just do sensitivity studies. So one of the sections at the very end is the sensitivity analysis discussion. So these again, and I apologize that I'm doing multispectral, but it shows up easier on charts and graphs. ETM plus, again, 1, 2, 3, 4, 5, 7. Blue, green, red, near-infrared. And then SWIR 1, SWIR 2, so 1.6 and 2.2 micrometers. The dashed line in all cases is the pre-launch calibration. The solid line is the average of all of the dots there, which is valid if you assume that you're not having any degradation. And then there's all the scatter that comes in. What you notice in band 3, that day 1500 effect. And it's the only band that really shows up, a little bit in band 4, but not much. And the question is what's causing the scatter? And I have spent the last 10 years trying to figure that out. And I still don't have a good answer. And as we go through this, that's really a good answer, because what it means is there's no single thing that's at a 3% level. That's roughly the kind of scatter you see there. If you do a 3% and then you have a Gaussian distribution, that's almost exactly what you get right there. And so that just means that there's not that one single factor that you can go in and say, all I have to do is fix that, and I go to 0.2%. It means I have to get rid of a little bit of aerosol problem. I have to get rid of a little bit of BRDF problem. I have to get rid of a little bit of this and a little bit of that. And that's annoying because it'd be much easier just to have to fix one or two things, but now it's kind of fun. But the real problem is we can never tell if we've actually made an impact. So we have to stop and go back and approach this from a physical problem. We have to stop and say, what is the right way to do this from the physics, and start doing it. And for people who are working in the National Metrologic Labs, the NMIs, that's second nature. For remote sensing people, no. We've been operating since the 1970s on making 20% mistakes and fixing them. And now we're in this 0.5% mode that's really frustrating for us. But what's nice is we think we know what's going on. And I love this because I had a student for a while that did this work, and what we did was we took all the measurements and took the standard deviation of the average of all the measurements, and that's the orange bars. And then I told them, go in and vary the atmosphere according to what we think our uncertainties are. And this is both a sensitivity and an error budget study in one piece. And they ran the code. It was 10 times or 20 times, six calculations. We showed that 5 calibrations was enough to get to where the standard deviation was the same as what 50 data points gave us. So the 6 random transfer calculations were Monte Carlo on the inputs. So we had our input for the given day, and then we said, go ahead and randomly sample all of the inputs according to what we think our uncertainties are, run the rate to transfer code again, and let's do the average at the top of the atmosphere and compute the standard deviation. And that's the standard deviation of the rate to transfer results. They are only statistically different in one band, band 1. Band 1 is the shortest wavelength. Now, for all the range of transfer people out there, you're going, well, that does not make sense, because the short wavelength is where the atmosphere plays a bigger role because of all these atmospheric influences. And I've got blue light, and I've got blue scattering, and I've got all these effects at the short wavelengths. But the reflectance of the surface, and I'm going to show this in one of my later charts, is what I call a magic reflectance. It's around 0.2, which means the atmosphere doesn't play a big role. So that's why the theory made the uncertainty much lower, which meant that this is dominated by my reflectance error. Because the measurements had the reflectance error, and the theory did not. And so by doing this calculation, I was able to go, all right, I know I can get rid of about 0.5 to 1% if I can somehow clean up my reflectance measurements in some way. And we just never figured out what was causing that influence. What was the feature of the reflectance characterization? Non-linearity, a sampling spatially problem, the panel calibration, and there would have to be a randomness to the panel calibration. But when you start doing this kind of combination of uncertainty, sensitivity analysis, error budget analysis, and comparison to measurements, you now start to get the insight into how to make the whole problem better. And really what we need is we need an on-orbit asset that's much better than the ones we have right now for us to figure out where the real problems are in this calculation. So the real answer is there's no clear cause for the outlier data sets. That's bad news because there's no easy fix. Instruments and personnel are still part of the problem. The real issue is everyone assumes independent and uncorrelated, and we know that it's not right. So we're going to have to move into the Monte Carlo world and do this properly to try and understand the non-independence between them. So for instance, when I make an error in my solar radiometer, it affects my retrieval of the aerosol distribution, the aerosol amounts, the water vapor, and the ozone. And they're all linked. It's not as though the ozone randomly varies and the aerosol amount varies. They go hand in hand. If the aerosol amount goes up, the ozone goes down, always. So having that in there means we have to go back one step. We can't just look at the inputs to the rate of transfer codes. We have to look to the inputs, to the processing, to the inputs to the rate of transfer codes.